Good day. These notes talk about determining parent acid and parent base from the salt. And I don't want you to get too bogged down on this. We do a hydrolysis lab, and that's the only time we're going to worry about parent acid and parent base. So I wouldn't panic about this stuff too much at all. It is not something I will test you on. When given a salt, it's possible to get a sense of how it will hydrolyze by knowing its parent acid and parent base. Well, you have to remember that these things come from, if this thing will cooperate, a neutralization reaction. So then we want to look at the strength of acids and bases and look at the possible combinations that we can get. And therefore, so let's take a look at these combos. If the parent acid that made the salt was a strong acid and the parent base was a strong base, the salt will be a neutral salt. So something like sodium chloride. The chloride came from HCl, a strong acid. The sodium came from sodium hydroxide, a strong base. And so we get a salt that just cannot hydrolyze at all. If we have a parent acid being strong and the parent base is weak, then the salt is going to hydrolyze as an acid. And if the parent acid was weak and the parent base was strong, then it's going to hydrolyze as a base. And if both things are weak, then we got to do a little calculation based on things like Ks and Kbs to figure out how it's going to hydrolyze. Like I say, this may look a little confusing. Don't get too panicked about it. We're just going to rattle through some examples, hopefully in a fairly tidy fashion. So when we look at the parent acid for this one, the Cl came from HCl, a strong acid. The K will have come from KOH. That's a strong base, and we know strong and strong means neutral. Now we look at this one. This is sodium acetate. The acetate came from a weak acid, CH3COH. But sodium came from sodium hydroxide, a strong base. So when we look at this, how will it hydrolyze? It's going to hydrolyze as a base because the acetate ion can accept a proton, and accepting a proton is acting like a base. Sodium sulfate, we look at the sulfate. We can argue it came from sulfuric acid. And this sodium hydroxide, well, we know sodium came from sodium hydroxide, strong base, so this should be neutral as well. CaBr2, well, that's group 2BC. We'll get that in a moment. We look at the bromide. Bromide, HBr, strong, strong. So it's got to be neutral. Next piece, the nitrate, strong, HNO3, the iron. Here we have a weak base. So overall, this will be able to hydrolyze as an acid, in large part thanks to the iron being able to donate a proton because it has water in its structure. We look at ammonium and we look at nitrate. Well, we know what nitrate is. We just had it. And now we look at ammonium and ammonia. Ammonia is a weak base. And so this will hydrolyze as an acid. The NH4 plus can hydrolyze. Lithium phosphate. So the phosphate we look at. So that will be able to hydrolyze as an acid. Lithium's group 1 from a strong base. So this will be, and this will be basic. The phosphate is going to be able to accept a proton. We're back to ammonium, and we have phosphate again, so we're combining those. They're both weak, and this is what we mean by calculations. We'd have to look at the Ks and the Kbs. And they're really close to being equal, but it's going to be slightly acidic. The ammonium slightly outpowers the phosphate when we look at those things. So that's our notes on determining parent acid and parent base. And remember, the only time you're going to use this is when you're doing a worksheet related to the lab. Alrighty.